Today we're going to talk about numerical integration, which means finding the area under a curve, under a function. So what is a definite integral? This is something you learn about in typically your second calculus class, where you're trying to find the area under a curve. How much, if you have a function as a function of x, you talk about the region under that curve, where the y is equal to 0 under this space from y equals 0 up to the function, this whole gray area. So that region between x equals a and x equals b is the area under the curve, or the integral of this function, the definite integral from this point to this point, that entire area. If the function is negative, the area can be negative. It seems a little odd to have a negative area, but it can happen for some cases. Even in engineering, you have negative values. And it's very important for biomedical engineering because it shows up in different applications. So you can talk about the strain energy in materials, or if you're looking at the total drug content when you give a drug to a patient over time, or the total amount of work done by the heart. There are different applications where you have to take a function and integrate it to back out another value that you're interested in. Now, how does this relate to biomedical engineering? Sometimes we can't directly measure a value from a simulation or a measurement, and some of our calculations we need to determine involve that integration, as I said. So if you have concentration fields or velocity fields, you may want to integrate them for certain reasons. If you think about an application where you have flow and concentration, you can see this concentration. The concentration is denoted by the color. The flow vector shows the x and y direction of velocity of the liquid in these different positions. So you can see it. Each point has a velocity, but each point also has a concentration. The concentration is a scalar value at each point, and the velocity is a vector value at each point. Now we are going to be interested in looking at some of the concentration values here. Now we're going to look at the concentration along this line, on this boundary of the flow field. So there's a high concentration here and a low concentration down here. For this example, if you just plot the concentration from this point to this point, and this is a ComSol simulation, we're going to learn more about ComSol later. If you plot that concentration from x equals negative 0.6 to x equals 0.1 along this position, you will get a nice line, and that line follows this simple equation. And it is in concentration, so the units on concentration are moles per meter cubed. So as you change x, you will get the different values and decreasing values of that concentration. This is called a cross-section plot. We'll learn more about that in ComSol, where you basically have a complex two-dimensional simulation, but you look at just plotting a value along a simple line. So for this, we're going to want to integrate that concentration. We're going to integrate along from A to B to find total amount of mass. So that concentration goes from negative 0.6 to 0.1, and that integral, which you basically can integrate this function to get a value, and you have to evaluate it from negative 0.6 to 0.1. So this is the derivative. If you take the derivative of this function, you end up with this value. So integrating this gives you this, and there's a relationship between integrals and derivatives. Now when you write the definite integral, you have boundaries. You know x goes from negative 0.6 to x equals 0.1. That means you evaluate this function at 0.1 and then subtract from it the value here on the right at negative 0.6. When you do that, you get an actual number. The integral of that is going to be some value moles per meter squared. Now why is it moles per meter squared? Well, if you multiply concentration times length, you're going to get basically moles per meter squared. Now, it's a little confusing to think about that, but that's called a flux. How many moles are actually not a flux because it's in our time, but it's basically moles per meter squared. But if you want to figure out the total amount of moles at that location, you'd have to go back to the geometry and think about this. Think about a rectangular tube in 3 dimensions where it goes up and actually in the z-axis as well. So you'd have to know the total area to find the total amount of moles. You'd have to multiply by the area of interest. So you'd have to know the y values and the z values to figure out the total amount of moles. There are a lot of common integrals, so if you have a constant, it's very easy to figure out the integral of that. Constant goes to 3x. But the definite integral, when you have values for x, can be evaluated very easily. The same thing for e to the x. So the integral of e to the x is e to the x because the derivative of e to the x is e to the x. You can always check your integrals when you take the derivative. Just like the derivative of x squared over 2, if you take the derivative with respect to x of x squared over 2, you get x. If you take the derivative of x cubed over 3 with respect to x, you get x squared. There are lots of tables that will help you look up integrals if you need to, if you don't know all the rules, to find an analytical solution. These are what we call analytical. In this class, we're only going to worry about numerical values. How do we numerically calculate the area under a curve for functions? Because a lot of times in engineering, we don't have nice, easy functions. Our functions may be very, very complex, or in this COMSOL example, may come from a value that's very difficult to get. We can't, often this doesn't fit a nice line. It might be a very complex value from the simulation. So our values, our function values, may not even fit a nice form like x squared or e to the x. So we want to integrate those values to figure out something of interest. How are we going to do that? We have that complex function. We're going to numerically integrate it from a to b. So we have this function, the blue line. So we're going to use the trapezoidal rule. We're going to do a single trapezoidal rule to illustrate this. But basically, how wide is your trapezoid? B minus a is the length. And if you multiply that by this function, basically the average of the function value. If the function evaluated a and the function evaluated b, take the average of that by dividing by 2 and multiply by the width of the trapezoid, b minus a, you get the area of this trapezoid in red. So for this example, our function is x squared. We know that the integral is 1/3 x cubed. If we do that numerically from 1 to 2, the value is 7/3. If we do it numerically instead of analytically, the analytical solution, the exact solution, is this value where you know the exact integral of that function, and you know starting and stopping, so it should be 7/3. This is the true solution. The analytical solution, when you put in numbers for the a and b, you get 7/3. Now, if you do it with a single trapezoid, you evaluate the function on the left and the right, and you plug in this trapezoidal function, you get 2.5, which is pretty close to what we got analytically. So even with a single trapezoid, you can get pretty close in some functions. For better approximation, we can take this value and we can integrate it with multiple trapezoids. How do we do that? Oops. We use this formula. This formula involves knowing how many subdivisions, how many trapezoids we want. N is the number of subdivisions. H is the spacing between subdivisions. So what does this mean? At x equals a, that's the starting point, x equals b, and each one of these subdivisions is size h. Now the function is evaluated at x equals a, but it's also evaluated here and here and here, and function evaluated at x equals b. So you have values at the left side, x equals a, values on the right side, x equals b, values of the function in between, these legs in between. And then we also have h over 2, and there's a 2 here. So why do we end up with this formula? I'm not going to go through the derivation, but basically this trapezoid has the left side and the right side. This trapezoid has the left side and the right side, so this value and this value and this value are going to get included twice. That's why we have 2 there. And we have to basically get the average between this guy, and this guy, the left side and the right side, the left side and the right side, the left side and the right side. That's what this summation of all those function evaluations divided by 2 is. Then you multiply by the average width of your trapezoid to get the total integral. Again, apologies. Here's a numerical example. We have x squared, and we want to integrate it from x equals 1 to x equals 2. So when we do that, We're going to assume n equals 4. We're going to subdivide into 4 trapezoids. If we know a equals 1 and b equals 2, we can calculate h because it's 2 minus 1 divided by 4, or 1/4. What does that mean? We have to evaluate x at x equals 1, x equals 2, or 1.25, 1.5, 1.75, and 2. When we stick those values into our function, we know the function, we know how to calculate h based on n, a, and b. We have to evaluate this function, and this is the actual x squared function over here. We plug and chug those function values into the formula. We know h is 1/4, there's a 2 there. We sum up all the values there, and we get a number of 2.34. Typically, you're going to end up making a table. The exact answer is 2.33, and our solution was 2.34, so it's very close to 2.33. If n equals 4, we get a very, very close approximation here. Now, when I make a table, I think about my x values, my a value, my b value, and I know I need 4 trapezoids. So you could do individual trapezoid. If you know the function evaluated at x equals 1, x equals 1.25, you can do those function evaluations and say, okay, the average of these two values is 1.28. The width of the trapezoid is 0.25, so I can calculate the area of the first trapezoid. You do the same thing for between 1 and 2. Evaluate the function here and here. You get the average value, multiply it by the h to get the trapezoid. So you get a column with trapezoidal values. You add these 4 values up for n equals 4, and you get 2.35, which is the same thing, pretty close to what we did here. So there's maybe a little numerical approximation there with rounding, but it's pretty darn close. Why do we do this? Again, ComSol simulations, when we're doing simple simulations, a lot of times we may want to have, if we have, say, a velocity profile across a blood vessel. The velocity is some value, it slows down near the walls, and it's faster in the middle of the channel. We can integrate this cross-section to find the average value, but you have to divide by the length, because remember, if this is velocity in meters per second, and you integrate with respect to meters, you're not going to have the right units. So you have to cancel the units so that you get basically the average value, which the average value for velocity should be somewhere like right in the middle. Alternatively, there may be cases where we've looked at applications of battery systems, and in a battery, the total amount of energy in the battery is calculated by amp hours, which is basically how many amps for how many hours can the battery provide. And if you integrate the current, which may be a function of time for a simulation, if you're going through a pacemaker or some application where you're looking at the charge from the battery, it may give you the current in amps as a function of time. If you integrate that over time, you'll find how many amp hours, or basically how much energy you used from the battery. Another application is drug delivery. I had a student that looked at modeling insulin injection into a patient. So if you have a control system that figures out how much insulin to put into a patient, you want to figure out how much insulin every day you're using. You may know the flow rate at each point in time, but you need to find out not just the flow rate, you need to find out how many milliliters of insulin you are using over the entire day. So you have to convert a value that may be the milliliters per minute into total milliliters for the entire day. And that involves integrating some complex numerical function or complex value of the simulation. Thank you very much.